Welcome everybody to the Green Bank Community Zoom. I am standing in for Jim Jackson. I'm a scientist here at the observatory, and I'll just quickly go over a couple observatory notes. We're observing this week. We've been shut down a lot of the summer to do maintenance. We've done really well in repairing the foundation areas that needed some work this summer, and we're observing right now through Labor Day, and next week we'll return to summer maintenance, and we'll be replacing 2 to 3 wheels in the coming weeks, and we'll be out of summer maintenance and return to normal operations on September 27th. This is just a picture up at Fantco up in Pennsylvania that shows they've already made all 16 wheels, and we'll be replacing them as bearings become available. So we'll replace some wheels, and then some bearings will get refurbished, some will be manufactured depending on the what's needed on the bearing. So, but all the wheels themselves have been replaced. So, have been manufactured. So we're long-term we'll replace all 16 of the wheels. So I'm gonna go ahead and hand this over to our speaker, which is Trey Wanger. And I'll go ahead and introduce you, Trey, or not. I'm trying to pull up so Trey Wanger. No, it says University of Wisconsin. Are you Wisconsin now?
I am, that's right.
Okay, cool. The Badgers. Welcome to the Big Ten or the Big 18 or something. I'm not sure if it's in the Big Ten these days. But anyway, Trey will be talking to us about cool diffuse ionized gas revealed by sensitive radio recombination line observations. So I'm going to hand it over to Trey, and you can go ahead and share. And as you're setting up, I'll just remind the participants, we'll do Q&A after Trey's talk, and just put it into the basically the chat window down at the bottom, and we'll address the questions at the end of the talk. So we can see your presentation. Go ahead and we can get going.
Great, thanks, Dave. Hi, everybody. My name is Trey Winger. I'm an NSF postdoc at the University of Wisconsin-Madison. And generally, my research interests focus on radio recombination lines as tracers of star forming regions, and then using those star forming regions to understand something about galactic structure. Today, however, I'd like to tell you a little bit about a different project that I'm involved in, where we have detected diffuse ionized gas that appears to be quite interesting and unique. And so I'm pretty excited to tell you about this project today. So first, a little bit of context here. We know that the Milky Way exists inside of a layer of diffuse ionized gas. This has been called the Reynolds layer by different people. But the nature of this component of the interstellar medium is pretty poorly understood. A lot of our observational constraints come from optical and infrared surveys, especially things like the Wisconsin H-alpha mapper, or WIM, which is an H-alpha all-sky map of the diffuse gas in the Milky Way. And it's from observations like these that we can start to learn a little bit about the physics of this component of the interstellar medium. For example, from some line ratios, you can derive things like the temperature of the plasma, and we get temperatures of about 8,000 degrees. If we assume that temperature, we can take our spectroscopic observations like H-alpha and derive some of the physics like the emission measure, or the integral of the electron density along the line of sight. And then if we combine other pieces of information, things like dispersion measures from pulsars and so on, we can learn things about the filling factor of this gas, which appears to be between 40 and 30%, implying fairly low densities. But ultimately, all of these surveys, all of these analyses are limited in different ways. WAM, for example, has fairly poor angular resolution. All optical observations tend to be have pretty poor spectral resolution. And then, of course, if you're working in the optical part of the spectrum, you have to worry about dust and how that's going to complicate your interpretation of these data. And so, we have kind of a holistic understanding, I think, of this medium in general, but the detailed understanding, I think, is still outstanding. And as a brief aside, there was this interesting paper by Ed Jenkins in 2013, which suggests that the free electron density in the warm neutral medium, the otherwise neutral gas, is actually, not zero. It has a small ionization fraction. And so one often wonders, how much of the emission measure that we're seeing from the the H-alpha emission, for example, is coming from otherwise neutral gas that's only partially ionized. And so there's a lot of outstanding questions about the nature of this gas, which is kind of the motivation for this project. In particular, it was the motivation for a survey that we carried out with the Green Bank telescope. This is the Green Bank telescope diffuse ionized gas survey, where we mapped a big chunk of the galactic plane and a few other star forming regions in radio recombination lines, a tracer of ionized gas at the radio part of the spectrum, where we don't have to worry about dust extinction and the complications there. And so using the GBT and the Vega spectrometer at C-band, we're able to observe 15 radio recombination lines simultaneously. As an aside, we also get a bunch of other things like higher order radio recombination lines and some molecular transitions as well. In total, we mapped about 50 square degrees, including a couple of star forming regions. And if we assume an electron temperature of 8,000 degrees for this gas, we're sensitive to emission measures exceeding about 1,100 parsecs per centimeter to the 6. So here on top, I'm showing some of our GDIGS data. This is a moment zero map, so an integrated intensity map over the full field of GDIGS. And on the bottom here is the same data, but overlaid in circles are the positions and sizes of known H2 regions. Of course, when we map ionized gas in the galactic plane, we're sensitive both to discrete star-forming regions as well as the diffuse gas, which is what we're ultimately aiming to trace. And it's from these data, it's from GDIGS that we learned a little bit more about the diffuse ionized gas. For example, if we assume that temperature of 8,000 degrees, then from the emission measures that we're able to derive from these data, we can infer densities of about between 1 and 30 particles per cubic centimeter. This is, assuming a path length. We have no independent constraint over the path length of this emission. And so these are kind of back of the envelope calculations. But a few years ago, Matteo Luisi and the rest of us explored the diffuse gas in the vicinity of W43 star forming region. And in particular, we developed a really simplistic one-dimensional kind of qualitative model for the brightness of the diffuse gas emission in the vicinity of these star forming regions in order to explore how much of the diffuse gas that we're seeing is actually just due to extended diffuse ionized gas halos around H2 regions. Certainly, some of the emission that we see in GDIGS and in these surveys is coming simply from diffuse ionized gas halos around H2 regions. This has also been seen in other tracers. For example, some Sophia and Herschel nitrogen data combined with some of our GDIGS radio recombination line data has really kind of formed the firm impression that at least some of this gas exists in a dense phase. It's a phase that people have been calling the dense warm ionized medium, gas that has densities much greater than the diffuse gas that we were thinking about before, with a little bit cooler temperatures, that exists in the vicinity of H2 regions. Ultimately, these kinds of surveys are limited by sensitivity. So the picture that we're kind of creating of the diffuse ionized gas in the Milky Way is complicated. It seems to be multi-phase. It seems that there's different kinds of diffuse ionized gas out there, and understanding, what this gas is, what it's doing, what its physical conditions are, and how important it is in the nature of the interstellar medium is really an outstanding question, which is what motivated the experiment that I'd like to tell you about today. So we thought it would be useful to do a very sensitive GDIGS-like experiment. That is, try to find radio recombination line emission, ionized gas emission from truly diffuse ionized gas. That is, gas that's not associated with nearby star forming regions, that's not part of this dense, warm ionized medium that exists kind of around star forming complexes, but really try to detect ionized gas that's completely diffuse and unrelated to star formation. So in that vein, we picked these two lines of sight through the galactic plane, one at a longitude of 20 degrees and one at a longitude of 45 degrees. These positions were picked specifically because they go through the galactic plane at a latitude of 0 degrees, but they're also very far from any nearby known star-forming regions, which might otherwise contaminate our radio recombination line detection. We then carried out what we think are the most sensitive radio recombination line observations ever. In total, our integration time per spectrum was about 300 hours. This is accounting for the fact that we observe 18 radio recombination line transitions simultaneously at around 10 gigahertz. We averaged them all together, giving us an effective integration time of about 300 hours, which leads to a RMS brightness temperature sensitivity or antenna temperature sensitivity of about 0.3 millikelvin. Here are the results. These are the two spectra that we obtained towards these positions. So here's at a longitude of 20 degrees, and here's at a longitude of 45 degrees. There's some interesting physics to note right away. First of all, the emission along both lines of sight is constrained to positive velocities only, which is telling us that all of the emission that we're detecting is coming from the inner galaxy. We're not seeing any ionized gas emission coming from beyond the solar orbit along these two lines of sight. Furthermore, the G20 spectrum shows a really interesting feature, which I'm going to be talking about a lot in this talk. It's this high velocity component, which is interesting because it has an extremely narrow line width. In fact, if you assume that the line is entirely thermally broadened, then we can set a very firm upper limit on the electron temperature at 4,000 degrees. This is already not in agreement with our canonical assumptions of the warm interstellar, of the warm ionized gas, which is a plasma that has a temperature of about 8,000 degrees. So this G20 feature is already interesting just looking at the data in this way. For a little bit of context, here I show the G20 spectrum that we obtained in black here, overlaid on the GDIGS survey, our full galactic plane survey, showing just how important the increased sensitivity of these observations was to detecting both of these features, both the broad, faint component and also the bright, narrow component, neither of which were detected in the original GDIGS survey. For a little bit of context, here are some longitude velocity diagrams showing in red the positions and line widths of our diffuse gas detections along these two lines of sight. And then in black points are the positions and velocities of known H2 regions around this part of the sky. And so this is interesting because it demonstrates that, some of this emission could be coming from, just the diffuse gas that exists in the vicinity of the galaxy where there are also star-forming regions. Consider, for example, the low velocity component along G20. The breadth of this, the breadth of the spectral line really overlaps the breadth of the positions and velocities of H2 regions in this part of the galaxy. This is also true for the high velocity narrow component, although there are much fewer star-forming regions in this part of the galaxy that are known, and there aren't any really in the vicinity of this component. Here's another way to visualize the exact same thing. So here I'm showing the spectra again, the radio recombination line spectra again for these two lines of sight. And now the points here represent the velocities of nearby H2 regions. In red, I'm showing all of the H2 regions within 30 arc minutes of this line of sight, and then in yellow within 100 arc minutes. So, for the low velocity broad component along G20, for example, there are a lot of H2 regions nearby. And one could imagine that there are leaking ionizing photons propagating through the interstellar medium and contributing to the ionized gas that we're detecting. That's probably not true for the high velocity component, where there really aren't any nearby H2 regions that could be producing those ionizing photons. Another thing we can think about is kind of a model of the diffuse gas in the vicinity of H2 regions. I mentioned earlier that in 2020, we developed this really simplistic kind of qualitative one-dimensional model for that to predict the brightness of radio recombination line emission in the vicinity of star-forming regions. This was fit to a star-forming region complex, W43. So it's probably not applicable everywhere. We probably shouldn't be applying this very simplistic model everywhere. Nonetheless, it does give us an opportunity to explore how leaking photons from H2 regions might explain the radio recombination line detections that we have along these two lines of sight. And so here on these spectra, I show in the colored curves here the models from this paper, which show the predicted radio recombination line brightness, assuming that all of that emission is due to diffuse ionized gas halos around nearby H2 regions. And like we saw before, there are some H2 regions in the vicinity of the low velocity component of the G20 spectrum here. And so it seems at least plausible that maybe some of that emission is due to diffuse ionized halos around some of those nearby H2 regions. For the high velocity component of G20, however, like I said before, there are really no H2 regions near that position. And so even with this pretty uncertain and poorly constrained model, it seems pretty evident to me at least that the G20 high velocity component really can't be explained by leaking photons from nearby H2 regions. And finally, for some context, we can look at some other ISM tracers. And so here are the radio recombination line spectra towards these two lines of sight, again shown in black. But now I've overlaid H1, 21 centimeter spectrum in red, and 13 CO emission from the GRS in magenta here. And so I don't know if this makes the situation easier to understand or more complicated to understand, but some things to note, for example, the H1 emission we see at negative velocities. Of course, we're seeing the H1 gas beyond the solar orbit, where we don't see any evidence for radio recombination line emission. But if we focus more closely on the high velocity component of the G20 spectrum, there's something interesting going on here. The radio recombination line emission velocity, the radio recombination line emission seems to peak at a velocity slightly different than that of the neutral gas and the molecular gas. I don't know what that's telling us. It might be telling us something interesting. So what's going on here? I'm really curious and excited to talk to some people in the audience today about their opinions, but here are some ideas that I've had and that I've compiled from the literature. One idea is that we could be seeing, specifically thinking about the bright, narrow feature for G20, we could be seeing the ionized skin of an otherwise neutral cloud. One could imagine having a neutral cloud that's being illuminated by ionizing radiation, and so we see just a partially ionized or a fully ionized skin of that cloud. The location of this line of sight in the galaxy might suggest that the ionizing source could be something in the galactic center. There are some interesting galactic structure arguments that could be made here, but I'll leave that for some future work. Another possibility is that we could be seeing cooling or condensing gas falling onto or condensing onto an otherwise neutral cloud. We have to recall that the recombination timescale for a plasma, for an ionized plasma, is much longer than the cooling timescale for that plasma, assuming the electron densities are less than about 1 particle per cubic centimeter. This was a hypothesis put forth by Dong and Drain in 2011, where they highlighted that H alpha and radio continuum data suggest that there should be a significant amount of ionized gas in what's called the unstable phase. There was a recent paper posted on the archive by Alex Lazarian's group talking about this as well, especially highlighting that turbulence can maintain the unstable gas for timescales much longer than the cooling timescale of the gas. That is to say, you can have these turbulent vortices on the surface of neutral clouds that are long-lived, and if that gas were partially or fully ionized, we would see it in this cooler and denser phase on the surface of these clouds. And so perhaps that is another explanation for the feature that we're seeing here. I was recently pointed to a paper by Israeli and Mahoney in 1990, which was looking at low-frequency radio continuum observations of other galaxies. And they put forth a hypothesis to explain kind of the low 50 megahertz flux densities that they were seeing towards some of these galaxies, where they claim that they could be seeing thermal absorption due to a cool plasma, gas with electron temperatures of about 1,000 degrees or so. So there seems to be lots of evidence that this kind of cool ionized phase of the interstellar medium exists, and perhaps these radio recombination lines here are some of the first direct evidence of the thermal emission from such a phase. So thinking to the future, kind of, where do we need to go? What do we need in the future to really solve this mystery and put better constraints on this phase of the interstellar medium and create a more holistic picture of the ISM in general? Well, one thing that would really help is low frequency radio recombination line observations. Pedro Salas is the PI of a program called GDIGS Low. This is a low frequency extension of the Green Bank Telescope Diffuse Ionized Gas Survey, where we're targeting radio recombination lines at 340 and 800 megahertz. It's a big project. It's not fully observed yet, but the benefit here is that with the low frequency radio recombination lines, we can start to break some of the degeneracies between the emission measure and the electron density. We can actually use the low frequency radio recombination lines to derive things like the electron density and the path length over which the emission is originating. This is a little schematic showing how these models work, showing different predictions for the spectral energy distribution of the radio recombination line emission for different physical conditions. The low frequency data, in particular, the 340 megahertz data, are really important because they provide the largest lever arm on the physical conditions of the emitting gas. Another path that we could and should go is to exploit the really sensitive many element interferometers that are currently under construction or will be in the near future. Things like CHORD, the spiritual successor to CHIME, or things like the DSA 2000. These telescopes are going to have really great large spatial scale sensitivity since they're compact interferometers. And so they'll really be sensitive to the large scale diffuse ionized gas emission in the galaxy. If we equip these telescopes with wide bandwidth receivers and correlators capable of processing all of the radio recombination line transitions that exist in those wide bandwidths, we would have some really exceptional tools for tracing ionized gas across the galactic disk. And so I strongly encourage anybody who has any influence on these experiments to consider the possibility of observing radio recombination lines as part of these experiments. So just to wrap up here, I hope I've convinced you that the warm ionized medium is probably more complex than what we would hope it is. It's probably multi-phase. There's probably diffuse ionized gas that exists in H2 region halos. There's probably unstable gas on the surface of otherwise neutral clouds. There's almost certainly some of that gas is almost certainly partially ionized. And then, I think there's plenty of evidence for a traditional WIM layer, a Reynolds layer type of gas in the Milky Way. What's important and what I want to note is that different tracers are going to be biased towards these different phases. And so when we take electron temperatures derived from optical observations and then just apply those electron temperatures to our radio recombination line observations, we might be lying to ourselves because the radio recombination lines might be looking at a different gas. Certainly true, for this G20 spectrum where the gas has to be colder than 8,000 degrees. So our radio recombination line observations are revealing some of these different phases of the gas, some of which is cold. That kind of challenges some of our canonical understanding of this phase of the interstellar medium. What is it? I have some theories. Maybe it's an ionized skin of a neutral cloud. Maybe it's some condensing or unstable gas on the surface of the neutral cloud. The jury's still out, and we're going to need some more data to kind of constrain the physics and get a better understanding of this phase. In particular, I think we need GDIGS low, especially the low frequency 340 megahertz data. That's going to be imperative to constraining the physics, the electron densities, and the path lengths of this emission. But then also future telescopes really need to exploit the wide bandwidth capabilities of their instruments in order to detect the ultra faint radio recombination line emission from the diffuse ionized gas in the galaxy. That's all for me. My name is Trey Winger. If you're hiring, please shoot me an email because I'm looking for a job. Happy to take some questions. Thanks.
Okay. Thank you for a very interesting talk, Trey. I remind the participants to go ahead and put their questions into the Q&A, and we've already have several questions that have come in. The first question is a very basic question. You already sort of addressed it, but I'll just go ahead and read the question. What is the ionizing gas? What is ionizing the gas? It's basically, do you want to say anything?
Yeah, for sure. I mean, that is a great question. It might seem like a simple question, but that's kind of one of the most important questions in this field. What is ionizing the gas? Is it UV photons that are leaking out of H2 regions? If so, how are they leaking out? Can we learn something about how those photons propagate through the interstellar medium? Is it cosmic rays? Is it evolved stars, white dwarfs and things like that? That's a fantastic question. And hopefully this work will illuminate the source of that ionization.
Okay, thank you. For the low temperature region in G20, is there enhanced H alpha as expected for low temperature ionized gas?
Yeah, that's a good question. And unfortunately, we can't answer that because the H alpha emission is dust extincted in this direction. What we're looking at is gas that's close to the galactic center, maybe even a little bit past the galactic center, and we just can't see H alpha emission through the galactic disk out to those distances. But it does raise the question, what fraction of the H alpha emission that we do see in the solar neighborhood from WAM or at high galactic latitudes, from WAM, what fraction of that gas is the warm 8,000 degrees canonical WIM, and what fraction of that gas is this colder component that's perhaps blended together along the line of sight, and so it becomes less easy to disentangle from the warm, broader line gas.
Okay, or it switched to a little more of a technical question. can the NVIDIA chips give extra wide bandwidth spectrometers?
Well, I'm not qualified to answer that question,
Okay.
but I'm sure some people in the audience here are.
Okay, yeah, I'm not sure. I know they're moving to this kind of technology, and I'm not. Okay, we'll just leave that as it is. Next question: could you comment on the contamination / detection of helium or carbon radio recombination lines, particularly overlapping the broad radio recombination line feature?
Yeah, that's a great question. And we certainly do detect helium and carbon radio recombination lines in addition to the hydrogen radio recombination lines that we see. So, you know, we have to consider that when we do the Gaussian decomposition, the modeling, and so on and so forth. In this case, though, you know, these lines are extremely faint, and the helium and carbon recombination lines are even fainter. And so I don't think we have any helium or carbon recombination line detections towards these ultra faint lines of sight.
Okay. How can the gas be turbulent yet have small velocity line width?
Well, so the line width that we're detecting for that narrow high velocity feature towards longitude of 20, the line width, the thermal line width, if we assume the line is entirely thermally broadened, would have to be about 4,000 degrees Kelvin. Certainly, some fraction of that is going to be non-thermal broadening, probably due to turbulence. What fraction of that broadening is due to turbulence remains a mystery, and hopefully is something that we can answer. For example, by having the low frequency GDIGS load data, where we can actually put constraints on the electron density and the path length. The path length there will be the important part.
Okay, that even pushes it down to potentially much colder temperature than the.
For sure, yeah, definitely.
Could you comment on the possibility of some side lobe contamination?
Yeah, we thought about that really hard because we were worried about that as well. Thankfully, the GBT has really great side lobe response because it's an off-axis instrument, and so we're not too worried about that. And then the fact that there really aren't any H2 regions close to our lines of sight on the sky really suggests that we're not seeing any side lobe stuff.
Yeah, I agree with that. Which molecules were observed in GDIGS? Any interesting results from the molecular observations? So.
Yeah, great questions. I can't remember all the molecules off the top of my head. I'll point you towards the GDIGS paper where we have a list of all the molecular transitions. And I don't think we've published any of those data yet, but there's some things coming.
Okay. The next question. Well, the questions are coming in fast and furious. This is great. Can you guess the filling factor of the narrow component you saw as an okay, and then as an aside, see recent paper by Abdi et al. As one of the several papers over the years using turnovers in the radio continuum spectrum of supernova remnants as a tracer of low density ionized gas, especially if cool. Has to fit does this fit into your big picture in any way, I guess is. So
yeah, the filling factor question is interesting, and no, we have no constraints on the filling factor, but we have some follow-up experiments in the works to try to get a better handle of this. We're taking some more GBT observations of some different positions close to G20. We also have some JWC observations in the works to hopefully get some line ratios and learn a bit about the physics that way. So, with some luck, we'll be able to put some better constraints on the filling factor. Regarding the low frequency turnover, we haven't really thought about that too much, but I pointed out that Israel paper from 1990 where they commented on this as well. And that's a good observational characteristic of cool ionized gas, is that you would get this low frequency absorption. So we should definitely see it towards this position if it exists. We should just look at those data or get some data.
Okay, and another question comment. G20 high velocity, the low temperature components, LSR velocity puts it at the tangent point in this direction, and the tangent point is 6 kiloparsecs from the sun. So H alpha emission from the gas would be totally extincted.
Yep,
so that's okay.
It's too far away.
Yeah. And then another comment. Herschel observed the carbon-2 158 micron line in G20. There is also a narrow line at high velocity coinciding with the radio recombination line detection. So just maybe.
Yeah, thank you for pointing that out, Jorge. There's something interesting going on here.
Yeah. And then, okay, we're getting, a couple more questions here. Oh, another comment. Sphere X should map the whole galaxy spectrum out to 5 microns and maybe detect bracket alpha from G20. So these are just some comments. I'm not familiar with Sphere X, so if you want to say anything there, these are just comments. And then we have another comment on, okay.
That's Tom Bania listing out. Those are the molecular lines
Oh,
that we
you're on it.
observed
Okay, yeah, I'm
with
like going.
GDIGS. Thanks, Tom.
Okay, I was like going to start. Okay, what is it? What's the questions here? Okay, thanks, Trey. Okay, any other questions? I had just a question on the chord. Is chord, it's going to work at the same frequencies as chime, the 400 megahertz?
I think that's correct.
Okay, and I know they're talking about putting a chord next to the chime outrigger here in Green Bank. That's part of their plan. So we're excited about that. And I hadn't thought about using that for a recombination line. So that's an interesting point. So I'm not sure if you're plugged in. I think they're still looking for funding and stuff. So I'm not sure who leads chord or whatever, but hopefully they have your science application in mind when they write their science case or whatever. So okay, any more questions? Okay, well, this has been a great Q&A session, and thank you for presenting today, Trey. We really appreciate it, and best of wishes and luck on the job searches. And that's a little bit of stressful time, but best wishes for that. So let's thank you everybody for attending. Next community Zoom will be September 11th. David Stark will be talking about H1 and break RGJ. Well, hold on. Shoot, now I have to look up the title. I apologize. Because it here I got the BRD galaxies, excuse me, using the GBT observations. So so thank you everybody, and we'll see you next time. Bye.
Thanks, Dave. Bye.
Thanks, Trey.